Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at the process design book by Turton as well as by Sider, and today we are looking at heuristics for reaction operations. So this is what the Turton textbook has for heuristics for reactors. So they start with, you have to know the rate of reaction, okay? You have to know that. So you're going to get that from literature, from laboratory, from a pilot plant, but you do have to know that. Then they talk about things like, okay, so what about catalysts? What assumptions can you make before you've, nailed down some of the design? Or what kinds of power input does it take to stir a tank reactor? And then they discuss various styles of reactors that you might have and what are some of those assumptions. If you look at Sider's book, he has a different set of heuristics. I think that the two complement each other. So his first is to select raw materials and chemical reactions that will avoid or reduce the handling and storage of hazardous and toxic chemicals. So, for instance, they look at manufacturing of ethylene glycol. And so we have the reaction set given here. And these are highly exothermic reactions. So you want to cool them. So you think, okay, well, then I'll put a water jacket on them. But if water accidentally gets into the ethylene oxide, then you end up with a seriously dangerous safety incident on the scale of Bhopal. So maybe that's not the best way to go. So some things that you might do, you could use chlorine and caustic in a single reaction and avoid an intermediate altogether. Or if you do have it formed, react it with CO2 to make ethylene carbonate, which is much less active and can be stored safely. They also talk about distribution of chemicals with reactions. So heuristic 2 says that you should use an excess of one chemical reactant in a reaction operation to completely consume a valuable toxic or hazardous chemical reactant. So this just makes sense, right? You can look at an SDS and figure out which chemicals are toxic or hazardous, and you want to minimize the chance of those getting out. So we'll put them in our reactor, and we want them to be completely consumed in the reactor if possible. When nearly pure products are required, you want to eliminate the inert species before the reaction operations if you can, unless the catalyst is going to be adversely reacted, okay? So then that maybe not. But you don't want to remove these if a large exothermic heat of reaction needs to be removed, because these can help ameliorate those thermal effects. So you need to decide whether or not you're going to remove your inerts before the reaction or after the reaction. And you're going to look at how easy it is to separate these things. How expensive will it be? And so you're going to need to look at the physical properties and do a simulation to get a quick idea of how easy the separation will be. Heuristic 4 says that you need to introduce a purge stream to provide exits for species that enter the process as impurities in the feed or are formed in irreversible side reactions. So the rationale here is that you're bringing stuff in. You can't let it just build up in the system, so you have to have a purge stream. Now that purge stream will be a vapor phase if it's a lighter species and a liquid phase for the heavier species. Next, they recommend don't purge valuable species, right? Or a species that's toxic or hazardous. So on those, we're going to try and recover them and sell them, neutralize them, whatever it takes, okay? will add extra devices so that we do not poison our surroundings. Heuristic 6 says byproducts that are produced in reversible reactions in small quantities are usually not recovered in separators. Okay? These will be purged, but they can be recycled to extinction instead of purging. So if it's produced in a side reaction, you can send it back into a recycle. Okay? Heuristic 7 is when you have multiple competing reactions, whether they're series or parallel, you want to adjust the temperature, pressure, and catalyst choice so that you get the highest possible yield of the desired product. And so the way you're going to do this is obtaining kinetic data to verify whatever assumptions you have made. So, for instance, in the manufacture of allyl chloride, reaction 1 produces my allyl chloride, but there's a side reaction, reaction 2, that produces dichloropropane, or I have a reaction where allyl chloride is an intermediate that produces dichloropropene. So I want to maximize reaction 1, minimizing reactions 2 and 3. So if we look at the kinetic data, the heats of reaction, the rates of reaction, and graph these as functions of temperature for the temperature dependence of K, what I see here is that I'm going to have K1 is the largest of the three in a small range. I certainly don't want reaction 3 to be the fastest, because then as soon as I make my product, it will disappear. And reaction 2 means that I've got a competing reaction, so I want it to be smaller also. So that minimizes my options of operating temperatures. And our final heuristic for this lesson is that for reversible reactions, consider conducting them in a separation device that you can remove products more or less as they are produced. This is a way of moving the equilibrium, okay? And so reactive distillation is one way this can be done. So we bring in our materials and we have a reaction zone, but this will eventually, whatever's left over will go out the top. This will hopefully all react away, and then just the water leaving. So I've got my product and my feed streams reacting, and so I end up with pushing my reaction more towards completion than equilibrium conditions would have predicted. So this concludes our look at reactor heuristics. In our next lessons, we're going to look at separations. Thank you very much for your time.